Okay, well, welcome back to this Tuesday that we're all pretending is a Monday. And they didn't even give us tacos. Taco Tuesday on Pretend Monday or something. So this last week in prep for Valentine's Day, we had our kids, we each gave our kids like $15 and set them loose in Target and said, you're going to be secret Cupid for one of your brothers for the next 8 days, and you get to use your $15 however you want to buy something for them, or you can do acts of service. You're not allowed to pocket the $15 and then do acts of service for the whole week, but and we made it so each of us was not assigned ourselves, but other people, and it was going great. But midway through the week, some strange things started happening. Like Amber had Dallin, the 13-year-old, but suddenly, in addition to what Amber gave him, a little can of beans showed up in his room, and we're like, I have no idea what this is about. And Amber couldn't say anything because it would totally blow her cover, right? Dallin, you're not supposed to have. Well, how would you know? And then Jack, the 15-year-old, randomly got a pizza cutter one day, and then one evening there was a bottle of Elmer's glue on Amber's nightstand. Just really strange things were happening at the same time as there was actually some good brotherly compassion going on. And it turns out the oldest, Nathan, decided that in addition to doing things for Jack, he was also going to introduce a little bit of mayhem into the experience. So he was randomly planting strange things throughout the house. Such a crazy sense of humor. His final gift to Jack was a card that Jack opened up, and it said, "Best grandma ever," and then in the inside, "Happy birthday." So totally made the experience kind of crazy. Fun, weird sense of humor. We found out this week that he got into BYU, so that's yay, finally. Yeah, we're not sure whether he's going to go here. It's not actually maybe that great an idea to go to university where your dad is also, but there is a modest tuition benefit. Plus, it's cheap for everybody anyway because of the church. So, but anyway, we'll see whether he comes or not, but we're glad that he has the opportunity. How it happened that Amber and I are old enough to have a child getting admitted to BYU is insane, because she and I actually met each other when we were freshmen, and there is no way that we feel like Nathan is prepared to meet an eternal companion. So we'll have to see what happens, but it's been an interesting ride, and you're going to turn around and it's going to be the same for you. You're going to be in your 40s, and your kids are going to be messing with your brain all the time and growing up and moving away. All right, let's see. I'm all distracted now. And we're back. Stereocenters. Okay. So we were talking about some of my evil tricks for concealing chirality. Remember, chiral molecules are molecules that are not the same as their mirror images. A molecule that is chiral must have an enantiomer. The enantiomer is the mirror image, but isn't the same thing. Two molecules that are stereoisomers but are not enantiomers, or that is, are not mirror images, must be diastereomers. So we've got those definitions down. The fail-safe for identifying chiral molecules is simply to draw the mirror image. But if you're going to do that, you need to be good at manipulating molecules in three-dimensional space, even if you're depicting that process on a two-dimensional page. So I could ask you, is this molecule chiral? Or I could draw the mirror image and ask, are these enantiomers? And that's sort of the same way, that's sort of the same question. To determine whether they're enantiomers, of course, you've got to be good at flipping molecules around. So there are two ways that you could see that these, or perhaps more than two, but two easy ways you could see that these molecules are not enantiomers of each other. And that would be to take your spatula and flip the molecule over pancake style. And when you do that, the OH group that was on carbon 2 pointing down and away from us is now pointing up and toward us, and the OH group that was pointing up and toward us on carbon 3 is now down and away from us. And lo and behold, you would see that the molecule is the same as its mirror image. So automatically that means no, it is not chiral. And are they enantiomers? No, they are the same compound. Now, the alternative way to see it, besides the pancake flip, is to try to find a conformation in which you can observe a plane of symmetry in the molecule. And it's not apparent necessarily at this stage, but if we rotate around that central carbon-carbon bond between carbons 2 and 3, we could redraw the molecule in this conformation, and at that stage it becomes much clearer that there is a plane of symmetry that makes these two OH groups identical, carbons 2 and 3 identical, and the methyl groups identical. And indeed, when a molecule has a plane of symmetry, that means by definition it must be its own mirror image, because you just move the plane of symmetry over and reflect the molecule through, and it's the same. So, and we do the same over here, rotating by 180 degrees, and that would allow us to draw the molecule this way, and again you see the plane of symmetry, and we could just simply move it over and it's exactly the same thing. So, yes?
You just had mentioned, so if it has a plane of symmetry, you know it's a mirror image?
Yes.
You're saying that like those are the same molecule, that they are like mirror images, so they could be like enantiomers?
So they are mirror images, but they are the same molecule, and therefore they are not enantiomers.
So you have a plane of symmetry, then you can rule out the fact that they're DNA.
Exactly. If you find a plane of symmetry, if two molecules, well, if two molecules are mirror images, but they both have a plane of symmetry, then yes, they cannot be enantiomers. They have to be the same thing. All right. So the principle is beware the hidden plane of symmetry. And the generalization we're going to make is if a molecule, why can't I press undo? If a molecule is not chiral due to if a molecule has, I'm really struggling, sorry, has a plane of symmetry in one conformation, it is not chiral in all conformations. And we'll put an asterisk maybe by all, and we'll make some really fine print below to say that that's based on the assumption that interchange between all of those conformations is fast. And that will be true in all of the situations that I will ask you about. There are some interesting molecules in chemistry where two different conformations about a sigma bond interchange so slowly that they actually are enantiomers of each other. It's kind of fun, but not fun enough to get into in this class. So what we mean by that is, even though the plane of symmetry isn't apparent in this top conformation, if we can find it in one conformation, it means the molecule's not chiral, period. End of story. Another place this kind of thing comes up is in drawing a chair conformation, which we may have discussed last time, I can't remember. As drawn here, it would be tempting to look at these two mirror images of each other and to say that they are enantiomers. Because if you tried to rotate them about, it would be difficult to superimpose them. It would be difficult to lay them on top of each other and have them be the same thing. And it's true that these two are mirror images, but they can interchange by ring flipping. And therefore, they're not enantiomers, they're the same molecule. That may not be totally clear, and you'd have to maybe do the ring flipping over here in this shape, and then rotate this around sort of in a clockwise direction and see that these two are the same. If you can interchange mirror images through rotation around bonds, and that process is fast, then the molecule is not chiral. It's easier to see this if you simply draw the molecule from above, in which case the plane of symmetry that shows you that carbon 1 is identical to carbon 2, the methyl groups are identical, becomes way clearer. So for 6-membered rings, perhaps better to draw the molecule from above. And then it can be much clearer, much easier to identify the plane of symmetry. A question from home is about chirality and what that means for the properties of a molecule. Enantiomers have identical chemical and physical properties except in chiral environments. And we'll talk about that probably next time. We probably won't get it today. All right, questions so far? Perhaps the worst and evilest and meanest way to try to conceal or to try to make these questions more challenging for you is to give them to you in Newman projection form. So here we go. All right, fun, huh? Is that molecule chiral? Another way of asking that is its mirror image the same thing? So there are a couple of ways to do this, and I feel like the best way is to get out of the Newman projection as quickly as possible. So to do this, we're going to put our eyes in the plane of the page, and we're going to look towards the bond between carbon 2 in the back and carbon 3 in the front. So here is the bond between 2 and 3. In the back, let's see, a methyl group on carbon 2 would be pointing upward in the plane of the page. There'd be a chloro group coming out at us, and a proton backing away from us. Let's see, on carbon 3, we would have a proton pointing downward, a methyl group pointing outward, and a chloro group pointing backwards. Is it chiral? Well, You could, from this stage, draw its mirror image, but you can make things a little bit easier on yourself by noticing that carbon 2 and 3 are attached to the same kinds of things. Both are bonded to a chloro, both are bonded to a proton, both are bonded to a methyl group. When that's the case, it helps to redraw the molecule such that the two methyl groups are lined up with each other, and I suppose you could say such that the methyl groups are eclipsed with each other. So I've kept carbon 2 in the same place. I've rotated the methyl group on carbon 3 back away from us. This brings the chloro down towards the bottom, but still oriented away from us. That would be the same as actually rotating such that, rotating the carbon in the front such that it was eclipsed with the carbon in the back. So methyl group, chloro, hydrogen, this is carbon 3. And then in the back we would also have methyl group, chloro, and hydrogen there. All right. Take a step back and look at those for a minute and convince yourself that we've drawn the same things. We haven't made any mistakes. We've just changed the shape, changed rotation around that carbon-carbon bond. If this is hard for you, it's okay. It just means you need more practice with the molecular model set. And if you practice, you'll get to the point where you can see it in your head pretty well. But it's going to be worth time now spent with the molecular model set developing those spatial reasoning skills, because you are not going to have enough time to practice during the exam. You'll want that skill to be cemented by then. Okay, so now let's answer the question, is it chiral or not? I've drawn this molecule in such a way that if there were a plane of symmetry, it would be obvious. The methyl groups are lined up with each other, but one chloro is up, whereas the other is down. So we would be sort of looking to see whether this line is a plane of symmetry, but it's not. Incidentally, if you want to, you can look in the Newman projection and try to see whether the plane of the page that bisects the bond between 2 and 3 is that, you can ask, is that, whoops, where'd that go? A plane of symmetry, and it's not, because what's in the back is not a reflection of what's in the front. Okay. Not a plane of symmetry. Okay, so the molecule isn't symmetric, doesn't have a plane of symmetry. The last question we need to ask is it the same as its mirror image? Or alternatively, now that we know there's no plane of symmetry, we can just ask, does it have stereocenters? If it has stereocenters and it doesn't have a plane of symmetry, it's got to be chiral. And indeed, carbons 2 and 3 are stereocenters. They're each attached to 4 different things. So yes, the molecule is chiral. Again, your fail-safe for chirality is to draw the mirror image and try to see and or convince yourself that they are the same. And it turns out you can flip this one over on the right a gazillion times and it's never going to line up with the one on the left. So the relationship between these two molecules is they are enantiomers. And yes, the molecule is chiral. So with Newman projections, easier to see chirality or lack thereof when you get to an eclipsed conformation. But if you want to avoid confusion, it can be good to redraw the molecule as though you're looking at it from the side. All right, other questions you want to ask? Yeah.
Just in terms of like practicing orienting myself and looking at The other one on the left is CH3, is that?
Sure. All right, cool. And I guess just to put a little bit more emphasis on the same point, if I change configuration at one of those stereocenters, I've now got a diastereomer of those two enantiomers. Is this one chiral? No, plane of symmetry down the middle, right? Yeah.
When you found the two stereocenters on that first molecule hydrogen, that meant it was chiral, because I also had more than one in my mind.
Yeah, if it has more than one, it might be chiral, but only if there's no plane of symmetry. So we had identified by moving the molecule around that there wasn't a plane of symmetry hidden somewhere, and therefore it had to be chiral if it had stereocenters. I'll show you, this is a Meso compound. It has stereocenters, but it is nevertheless not chiral because it is the same as its mirror image. If you look at a Meso compound down the carbon-carbon bond in one of the three possible eclipsed conformations, everything in the front will mirror everything in the back, and the page itself is the plane of symmetry. And so if a molecule is drawn for you in a Newman projection, you may want to just draw it in as many of the eclipse conformations as you can to look for planes of symmetry. Alternatively, draw it from the side, and it tends to be simpler from that direction. Okay, so terms. A Meso compound is a molecule with stereocenters that is not chiral because it has a plane of symmetry. Diastereomers, you will note, are different at one but not all, at least one but not all stereocenters. Is it safe to say that if there's no plane of symmetry, the molecule is chiral? If it has stereocenters, then yes. There are some weird, chirality is essentially a geometrical thing, so I'm imagining there's some exception to that, but I can't think of one off the top of my head. All right. So now I think it would be useful to just work briefly on how we talk about stereocenters. Because this can be a useful way to distinguish enantiomers from diastereomers if you can do this correctly. So we're going to use the stereochemical terms R or S to describe what's called the absolute stereochemical configuration of a stereocenter. What do we mean by absolute? Well, notice that whether at a stereocenter, whether chloro is up or down depends on the shape I draw the molecule in. And so that means that using things like the up stereoisomer versus the down stereoisomer is not really going to be that useful to us. So we're going to have a way of assigning the two possible ways a stereocenter can be based on the same priority rules that we used to determine E and Z configuration. So let's actually start with that Meso compound where you've got the two chloros. When you're assigning stereochemical configuration, it can be useful to draw in the hydrogens that are not shown but are implied at a stereocenter. And let's just say A and B, and we'll start with stereocenter A. So we're going to apply our R versus S assigning by considering the four different things attached to the stereocenter. That's what makes it a stereocenter. It's a carbon sp3 carbon bonded to 4 different things. And we're going to compare them atom by atom in order of atomic weight, which we've done before with E and Z. So as I look, I've got chloro of the 4 things I've got attached to the stereocenter A. 1 is chloro, 2 are carbon, and 1 is hydrogen. So if I can rank the lowest or the highest outright, I should make that assignment. Hydrogen is the lightest, so that is priority 4. Chloro is the heaviest atom. Chloro beats carbon, so that is priority 1. Now I've got to decide, does carbon beat carbon? It's a tie. So now I simply do the tiebreaker procedure and I consider what each is bonded to. On the left, the methyl group is bonded to 1 carbon and 3 hydrogens. In contrast, carbon B is bonded to a chloro, 2 carbons and 1 hydrogen. Chloro beats carbon, so atom B has priority 2 and methyl has priority 3. Now, I'm going to ignore atom 4 for now, and I'm going to draw an arrow from 1 to 2, and then from 2 to 3, and then 3 back to 1, completing the circle. And I'm going to notice 2 things. First, going from 1 to 2, 2 to 3, and 3 back to 1, that rotation from our perspective is counterclockwise. Second, I'm going to note that the priority 4 group is pointing back away from us. Priority 4 group is hydrogen. When those 2 things are true, then the stereocenter is S. Okay? When the priority 4 group is away from you, counterclockwise is S and clockwise is R. Okay, questions so far? No? All right, we can use a similar argument for stereocenter B. There's a proton in the back that's implied but not shown. Chloro is 1. 2, 3, methyl group is 3, hydrogen is 4. 0 to 1, or sorry, 1 to 2, 2 to 3, 3 back to 1. That is clockwise, and proton is, or our priority 4 group is back. Therefore, the stereocenter is R. Okay. Now, your text teaches this a little bit differently. Your text teaches you to always draw the lowest priority group in the back, and then it teaches you that clockwise is R and counterclockwise is S. And that's true, but what if you have a situation like this where maybe maybe for one of these stereocenters, hydrogen is up, okay? Now, your text would say, well, simply redraw the molecule such that hydrogen is back, and then go from there. And you can do that, and that will work, but you better be very good at manipulating molecules in your head and drawing them on paper, because if you redraw it and screw up the stereochemical configuration, even if you assign it correctly, you're going to get the wrong answer. So to mitigate that risk, one of the things you can do is just to leave that priority 4 group in place. Assign priority as you normally would. I will do that here, and then later you can follow. Later, if you want to, you can convince yourself in the notes that I'm right. The rotation from 1 to 2 to 3 is clockwise, but proton, our priority 4 group, is up, not back, is in the front, not in the back. So it would normally be R, but it is now S. You switch when the proton is in the front and not in the back. this relates to the fact, and it's kind of dumb, but if you look at a certain rotation from above, it looks like it's clockwise, but if you do the same thing and look at it from below, all of a sudden, I'm going the same direction, but it looks like it's counterclockwise. What I always say in my brain when I'm assigning configuration, okay, rotation is clockwise and proton is back, so that means regular rules apply, so that would be R. And then for here, for example, I would say to myself, okay, the rotation is clockwise, but proton is up, so it would normally be R, but since proton is up, it's S. And that's sort of how I assign stereochemical configuration, and that way I don't have to redraw the molecule. If group 4 is in the back, then clockwise is R and counterclockwise is S. If group 4 is in the front, then just switch. Okay? Now, you want to practice that because R versus S questions are easy to ask on an exam. You'll encounter probably as many of those as you did E versus Z. For questions where it's flip a coin, R versus S, it's possible to get the right answer for the wrong process just on accident. Even if you don't know what you're doing, you're going to get it right 50% of the time. So you'll need to, if you want to get it right 100% of the time, you're going to need to interrogate your process as you're getting things wrong to make sure you understand why you got it wrong and make sure you're applying the rules correctly. Okay. So that's R versus S. Anything else you want to say about that? I guess it may be useful to just point out then that you can use R versus S to tell whether molecules are enantiomers versus diastereomers. So enantiomers will have opposite stereochemical configuration at each and every stereocenter. So the enantiomer on the left has two S stereocenters. The enantiomer on the right has two R stereocenters. By virtue of the fact that each of these carbons 2 and 3 are attached to similar things and they're stereoisomers, and their configurations are opposite at each and every stereocenter, they have to be enantiomers. Note that the mesodiastereomer has SR configuration. Different at one, but not all. All right. So I'd say that's worth practice. Yeah, go ahead.
Is it true that if there are 3 stereocenters, for it to be an enantiomer, they need to alternate R and S?
Is it true that if there are 3 stereocenters in order to be an enantiomer, they must alternate? No. That will simply depend on the structure of the molecule. I think there's probably a case where it would be that way, but I can draw a molecule with 3 stereocenters that doesn't alternate at all. So the stereocenters in this molecule are these 3. I'm not sure whether it alternates or not. That molecule is chiral. It's got 3 stereocenters. It doesn't have a plane of symmetry. If I were to assign stereochemical configuration, I would say this one is R. This one is S. And 1, 2, 3. This one is also S. So no, they don't have to alternate. It just depends. Other questions? All right. We didn't quite get this far at noon, so I'm hesitant to jump too far ahead, but I do want to tell you a story about why you should care about chirality. Years ago, and I believe the drug was approved in 1998, a drug with the brand name Prilosec came on the market, and it was a proton pump inhibitor that was prescribed for acid reflux and heartburn. And to this day, it's still used in hospitals. You can still buy it at Costco. It was, I think, I'm going to get this wrong, I believe it was developed and marketed by the company AstraZeneca. You've heard their name recently, probably because of COVID vaccine development. In any case, this molecule has a stereocenter. It's not actually apparent from the way I've drawn it. The sulfur is attached to three things and a lone pair, and it turns out that sulfurs with attached to three things plus lone pairs can be stereocenters. Typically, nitrogens that are attached to three things, three different things, and one lone pair are not stereocenters because they rapidly invert through sort of umbrella action, but it's a lot slower for sulfurs for reasons you don't need to worry about. So just accept for the sake of argument now that that's a stereocenter. Okay? One stereocenter which makes the molecule chiral, and it turns out that making a molecule with one stereocenter and making it in a pure enantiomeric, making it as just one single pure enantiomer is kind of difficult. In nature, as far as we can tell, there is no ex nihilo creation of stereocenters. You either get them from existing stereocenters or you use existing stereocenters to bias some synthesis process towards one enantiomer versus the other. And so chemically, it is easier to prepare not just one pure enantiomer, but the one-to-one mixture of both enantiomers. Now, that may not make a lot of sense now, and that's because we haven't done any reactions yet. We will, and you will see clearly soon that if your molecule that you start with is not chiral, the products either have to be not chiral or you have to make a one-to-one mixture of enantiomers. The one-to-one mixture of enantiomers is called a racemate or a racemic mixture. And sometimes when we want to save time, we'll just draw one of them and use a plus-minus symbol. That refers to an interesting property of chiral molecules to rotate plane polarized light. One enantiomer rotates clockwise, the other counterclockwise. Has absolutely nothing to do with R versus S. And it's some physics is involved, and we won't talk about it that much. But in any case, it was cheaper for AstraZeneca to prepare this one-to-one mixture of enantiomers, which they marketed as Prilosec, and the generic name is omeprazole. I don't know who makes up these names. They have focus groups, and it's like just sort of cool. They go for a coolness but not gross factor. And sometimes they succeed, sometimes the names aren't pronounceable. By the way, just if you happen to be watching, maybe Hulu advertises to me in a different way than it advertises to you because I'm in my 40s. But I see lots of commercials for various irritable bowel things and cancers and other things. And a lot of the drugs have MAB at the end. That means monoclonal antibody. That's a biological drug. In any case, omeprazole, prescribed for heartburn, proton pump inhibitor. So you may not know this, but it takes a long time to develop drugs. You have to not only invent it and develop the synthesis and make a lot of it, but you also then have to do the clinical trials. And it's been a real tour de force this year for the COVID vaccine clinical trials to happen so quickly. Normally this takes a lot of time. In the United States, patent law protects the inventor as the sole licensee of the technology for a certain number of years. And I believe it's 17 years after patent filing. Patent filing, not drug approval. So usually by the time a drug is approved for use, you've got maybe anywhere between 10 and 14 years of exclusive rights to make and sell that drug, and you've got to recoup the billions of dollars you invested in making that drug. And they call it the patent cliff when the patent expires and suddenly other companies can start making your drug for a lot cheaper and the price goes down and you stop making money on it. About the time I was in college, Lipitor, Pfizer's anti-cholesterol drug, went off patent. And this was a multi-billion-dollar blockbuster drug, and the revenue from that dried up very quickly. So drug companies do not like this. And so they've gotten a way of getting around it in some cases. And that is that instead of selling you the cheaper one-to-one mixture of enantiomers, they will now give you just one of the two enantiomers. They called this S-omeprazole because it was the S enantiomer, and they marketed under the name Nexium. And I still remember advertisements in the early 90s about Nexium, the purple pill. And so here's an interesting question. They imagine that you're a physician and a drug representative comes to you and says, hey, you know that omeprazole that you've been prescribing for heartburn? You know how it's really cheap and available right now as a generic drug? You don't want to be prescribing the cheaper drug to your patients because we have this better, pure enantiomer, the active enantiomer, and you should pay us a premium for that drug, which we now, because it's a pure enantiomer, we can now get approved for another X number of years in patent protection. They call this the chiral switch. All right. Now, presumably to do this, they would have had to demonstrate that both the one-to-one mixture of enantiomers and one pure enantiomer were both safe, okay? So assume that one of them is not toxic. Is it even reasonable to suspect that one pure enantiomer might be more effective than a one-to-one mixture of enantiomers? What do you think? I told you enantiomers have identical chemical and physical properties, but not biological properties. Why don't they have the same biological properties?
Because maybe your biological environment, one of them responds and the other one is.
Okay.
Or is enzymes able to attach to it?
Say that again, sorry?
How it connects with enzymes?
So if the two enantiomers have different shapes, how they interact with enzymes could be different. Okay, but why is that? Go ahead.
The shape of receptors, it's only for one of the enantiomers.
Right, the shape of the receptor itself is chiral. Okay, the molecules that do a lot of the work in cells and in biology are proteins. I'm drawing just a small subunit of a protein. These have stereocenters. They are chiral. That's a short 2 amino acid segment of a protein. Carbohydrates, like glucose, are chiral. We drew glucose before when talking about chairs, but we didn't mention that it's a chiral molecule. Your body uses amino acids all of the same chirality and sugars all of the same chirality. So you are one enantiomer of two possibilities. All right, now why should that matter? Well, to see that this is the case, consider going to shake hands with somebody. You're now having a interview. Maybe suppose you've already paid the application fee and then sent in your secondary application fees where they ding you twice for your applications to medical or dental school. You finally get an interview. You go in to shake hands. The interviewer offers her right hand, and you go and offer your right hand, firm handshake. Everybody's happy. You sit down and have a great interview. Suppose instead of offering your right hand to her right hand, you offer your left hand. What have you got then? Sort of awkward, maybe fish kind of, what, am I supposed to kiss this or something kind of handshake, right? A handshake of a right hand with another right hand is a diastereomer of a handshake of a right hand with a left hand. They're different, okay? Now, you could say that brains are chiral too, and even if you tried the left-on-left handshake, it could be weird if you're not both left-handed and whatever. The point is, biology is chiral. And two chiral molecules, and one chiral molecule can distinguish between two enantiomers, much in the same way that your right hand can distinguish between somebody else's right hand and their left hand. Okay? So, it's possible that whatever this molecule does, it inhibits a proton pump. It is possible that only one of these two enantiomers is in fact the active compound, okay? And the other one maybe doesn't do anything. In the same way that a right-on-right handshake is official, but right-on-left is kind of weird, at least in our Western sort of culture, which is why we don't do handshakes anymore. We sort of go with fist bumps or elbow bumps, or Governor Herbert recommended that we adopt the bow as a sort of way, and culturally, maybe we should. That's a lot less germy. The other thing we should get rid of is blowing out birthday candles. Can you even imagine? Can you imagine all the slobbering we used to do in the name of birthday celebration? There's a lot of things going on in the chat about whether or not you can get into medical versus DO schools depending on your right or left-handed. It's getting completely out of hand. So if I told you that, what if the pharmaceutical sales rep says, oh, well, you know what, a 50 milligram dose of Nexium is just as effective as a 100 milligram dose of Prilosec. Should you be impressed? Suppose enantiomer A versus enantiomer B. Suppose that enantiomer A is the active one anyway, and that enantiomer B, suppose, just doesn't do anything. Then how much of the active enantiomer does a 100 milligram dose of the racemate get you? Just 50 milligrams. So not impressive at all that 50 milligrams of the pure stuff does the same thing as 100 milligrams of the 50-50 stuff. Now, what is the end of this story? Well, it turns out that AstraZeneca was able to argue that for some people with a certain variant of a cytochrome P450 enzyme, the esomeprazole was metabolized differently than the R enantiomer and could therefore potentially be better. But it's legitimate that enzymes that are chiral might modify and metabolize one stereoisomer versus another better, but it was just a modest benefit. Nevertheless, they could claim, hey, we've got this new pure drug, and you should prescribe it, and we'll continue to make good money on it. There are other more interesting stories that we don't have time for, though your text will point out the tragedy of R versus S thalidomide. Thalidomide is an antiemetic drug prescribed in many cases early in years ago, 50 years ago, for morning sickness. But the R enantiomer was a teratogen, a mutant, a mutator of fetuses. And it turned out that even if you could just give the pure enantiomer, once in the body, it could actually chemically interconvert between the two. So there was no way to avoid getting the teratogen in there with disastrous consequences. So stereochemistry matters. I want to say more about diastereomers and biology, but we'll have to save that for next time. And just everybody dab instead of handshakes. Is that what we're going for now? Did I do that correctly? I don't know. Okay, it's okay. I'm not going to try. See you next time.